2 kilogram of refrigerant 134A initially at 2 bar and occupying a volume of 0.12 meter cube undergoes a process at constant pressure until the volume has doubled. Determine the work and heat transfer for the process, each in kilojoule. From statement, the mass is 2 kilogram. 2 kilogram. And pressure initially is 2 bar. And this is equivalent to 200 kilopascal. Volume is 0.12 meter cube. So V1 is 0.12 meter cube. And then the process is at constant pressure. So therefore, P2 will be similar to P1, which is 200 kilopascal. And the volume double, so 0.12 goes to 0.24 meter cube. Schematic, initially pressure is 200 kilopascal and volume is 0.12 meter cube. Because this is a constant pressure process, so it must be a piston cylinder device in which the pressure remains constant when the piston moving up. So then after that, the volume is double and pressure remains constant, 200 kilopascal. So for state 1, volume is 0.12 meter cube and pressure is 200 kilopascal. Therefore, your specific volume is V1 divided by M. V1 volume is 0.12 divided by 2 kilogram. And your specific volume is 0.06 meter cube per kilogram. So if you look at the steam table for R134A and look at 200 kilopascal, and this is Vf and that is Vg, and your volume, your value of 0.06 is in between Vf and Vg. Therefore, your phase is saturated mixture. And then for V2, you have a specific volume 0.24 divided by 2, so you get 0.12 meter cube per kilogram. And pressure remains the same, 200 kilopascal, so pressure is the same. This is Pf, this is Vg, and your value is above Vg. 0.12 is above 0.099867. So the state is superheated vapor. Now you need to write the energy balance for the process. E in minus E out equals to delta E system. E in is Q in plus W in, E out is Q out plus W out, delta E system. Q in minus Q out plus W in minus W out. There's no work in, there's work out because of the boundary work, the piston moving out. Delta E is the increase of energy, which is delta U in the piston cylinder device. You have Q in, you have Q out. Since you don't know, because which, because the problem does not specify Q in and Q out, you can write them as delta Q, the change of heat. Yeah. So what we want to find is the change of heat, which is delta Q. So delta Q equals to delta U from here plus boundary work, WB. So boundary, because this is a constant pressure process, so boundary work is P naught V2 minus V1. So P is the constant pressure, which is 200 Pascal. Volume 2 is 0.24 minus volume 1, 0.12. So you got 24 kilojoule. And for delta U, you have U2 minus U1. For U1, you need to find the quality. So we know V1 is 0.06. So from the steam table, we use the equation V equals to Vf plus X Vfg. So from there, you can write X is equals to V minus Vf divided by Vfg. So it gives you a value of X, which is 0.5978. Once you know X, you can find the value for U1. You know X, you can find the value of U1 from UF here, 38.28 plus UX times UG, 186.21. So this gives you the value for U1. For V2, the specific volume is 0.12 and it's superheated. So you go to pressure of 0.2 megapascal and then look for 0.12, and 0.12 is between 0.11874 and 0.12322. So you have to do interpolation because you know the value of the value of specific volume. So you can do the interpolation to find U2. So after the interpolation, your U2 would be 257.37. So delta U is U2 minus U1. So delta U2 minus U1 times M, because this unit is kilojoule per kilogram, with times mass. So you got 215.54 kilojoule. So your delta Q is delta U plus boundary work. This one you calculated earlier, this one is from here. So therefore your final answer is 239.54 kilojoule.